Right, welcome back to a discussion of synchrotron radiation, wherein we've looked at the dynamics of a single charged particle in a magnetic field, and then we have looked at the radiation power that we get out. So what we did last time in the other previous video before this is we wrote down the radiation power, the energy loss rate of a charged particle in a magnetic field. We simply used Larmor's formula for that. I just wrote down Larmor's formula, and then we had to do a little Lorentz transformation of the acceleration, which is actually in the instantaneous stress frame, into our lab frame. I don't have that here, but we had that last time. And then when you put in the actual acceleration for our case, which is a charged particle in a magnetic field, which you derived in the first time, then you get the total radiated power. And we wrote down two expressions for the total radiated power. One is in terms of the pitch angle between the particle, so we have the magnetic field in some direction, and we've got the particle moving at some angle alpha with respect to the magnetic field. So this power is in terms of the pitch angle, or you can average over the pitch angle, which is relevant if you've got scattering going on, the particle pitch angle is changing, or if you're averaging over multiple particles, as we'll do later. One thing that I've added here that I didn't have last time is these minus signs, and that's just to indicate that the power that's radiated is energy that is lost by the particle. So in other words, this thing on the right side is the energy that's lost. So this dEdt is negative, so the particle's energy is going down. And the radiated power is minus dEdt, so it's positive. So the radiated power is positive, but dEdt itself is negative. And these minus signs were not there last time. For clarity, I just kept them separate, but here I've added them back in. Okay, so in that context, something to keep in mind is that this radiated power is proportional to gamma squared. So P rad, which is just dEdt or minus dEdt, is ddt of the energy, which, remember, the relativistic energy now has gamma, so it's gamma mc squared is the total energy of the charged particle. And so that radiated power is energy that is now lost by the particle at this rate. And so this rate is proportional, as you see it from here, to gamma squared, which means, or more specific, to minus gamma squared, right? So the ddt of gamma is proportional to minus gamma squared, which means that a particle, these brackets are superfluous and maybe just be confusing, so I'm going to remove them. So d gamma dt, which is the rate of change of the Lorentz vector of the particle, is proportional to gamma squared, which means that the higher the Lorentz factor of the particle, when it enters this region of magnetic field, the faster it loses energy through this process. So more energetic charged particles, or with high Lorentz factors, lose their energy faster through synchrotron radiation. And this is going to be very important when we are discussing synchrotron cooling, because we'll have a distribution of particles, and the most energetic particles will lose the energy fastest, and so the distribution is going to start having breaks in them, and that comes about because of this effect. And then before, so the plan today is to talk about the spectrum of this radiation from a single charged particle. Before we do that, I wanted to discuss one kind of corner case, which is this aspect of cyclotron radiation. And I wanted to mention that just for completeness, and it may be relevant in some cases, depending upon what you're doing with this physics. And so cyclotron radiation is relevant in the case where beta, which, remember, is V over C, is much less than 1. So a particle is fast, but it is not ultra-relativistic. And so in those cases, we can take gamma, the Lorentz factor is of the order of 1. And in this case, really, all I'm going to talk about, I'm not going to talk about all these powers and such. These are the same similar expressions that are relevant. But I'm going to talk about the polarization of the cyclotron radiation that you get. And this is, so let's just look at the dynamics. So let's say the magnetic field is oriented, and so when we talk about polarization, we're talking about the polarization of the radiation. The orientation of the line of sight with respect to the direction of the magnetic field becomes important. So let's say we're looking at the magnetic field, it's pointed into a line of sight. So we're looking at a system, it's got a magnetic field that's kind of poking out of it. In that case, the charged particle, as you know, will make circles, and so the projected orbit or trajectory of the particle is going to be a circle in the sky, I guess, to whatever you're looking at. The acceleration is going to be a perpendicular pointed inwards. It's a centripetal acceleration that keeps it going around in the circle. And so regardless of where the particle is in its orbit, the acceleration is always pointed inward. And so the polarization that you get out of this is, if you really want to calculate this polarization from first principles, you can use the linear wave-shape potentials. You can figure out the direction of the electric field with the R cross A retarded time. If you've seen those, if you're familiar with those, that's fine. But really, the symmetry of the system kind of gives it away. So in this case, you have a circular orbit, and so the polarization that you get out is going to be circular polarization. So in this particular case, the light is going to be circularly polarized. And then depending upon the direction of the magnetic field and then the direction of the orbit, you can get right or left circular polarization. The other case is, or the other extreme case, is if instead of the magnetic field being aligned to our line of sight, the magnetic field is transverse to our line of sight. In another case, which I'm drawing here, the acceleration vector, so this circle basically turns on its side, it's now on its edge, and so the acceleration vector is going to be in the plane of the sky. So the acceleration vector is always going to be either pointing up or pointing down, and with some magnitude with a plus or minus sign. Right, so a perpendicular is going to be pointed up or down. And in this particular case, as you can imagine, the polarization that we get out is linear polarization. So in general, the polarization of cyclotron radiation can be anywhere between circularly polarized to linearly polarized, and it depends, the polarization depends on, or the polarization type depends upon the angle that the magnetic field makes with respect to the line of sight. So the spectrum of this radiation, which I shall write down over here, has a series of harmonics, and it looks like this. So these are the locations of the harmonics of the spectrum, and L is the harmonic number, the order of the harmonic, is L times nu g, which remember is the gyro frequency. This is the linear gyro frequency divided by gamma, the Lorentz factor, which is of the order of 1, divided by 1 minus V parallel over C cos theta b. And so theta b is the angle that the magnetic field makes with the line of sight. So here theta b is 0, and here theta b is 90 degrees or pi. So theta b is the angle that the magnetic field makes with respect to the line of sight. So you can see here is an excellent example of a spectrum that depends upon the orientation that the magnetic field has with respect to the line of sight. So it's a cool way of determining the magnetic field orientation with respect to a line of sight if you measure the polarization. So in general, the polarization will be somewhere between linear and circular. So in general, you get elliptical polarization. This, by the way, is equation 8.11 of high energy astrophysics. And it's the series of harmonics because actually it turns out that the pattern isn't exactly a complete circle because of some relativistic effects. So you can see the discussion of that if you're interested in that part of the high energy astrophysics textbook. So this completes our discussion of the single particle dynamics, the single particle radiation power. And the next thing we're going to look at is the spectrum that we get out from a single particle when it is relativistic. So this is the non-relativistic version. I can draw it. This has a spike and then a series of harmonics which kind of get wider and wider. So I'm now plotting versus frequency the radiation power. And these are these different harmonics. And actually, you can show, it turns out that this becomes a power law when you add it all up. At lower frequencies, of course, you get these spikes, and then it kind of averages out into this power law. So that's the, I'm going to take this off. The discussion of this spectrum is more clearly, there's more detail about this in the high energy astrophysics book. Okay, so now let's move on from single particle powers to single particle spectra. And so that's a discussion of the spectrum of synchrotron radiation. So single particle spectrum. Okay, so now there are some relativistic effects that we need to account for. So I'm going to make some diagrams. We'll have some geometry to take into account. So we have our charged particle. It's moving in this spiral. Let's take a section of that spiral. And let's say we're looking at this small section. And in this section, the acceleration vector is pointed that way. So here is our A. I'm putting primes on it to indicate the rest frame. This will become clearer as to the different frames will be clearer in a second. And if we zoom in to this little box, this region, then the particle is instantaneously, let's say, moving in that direction. That's our v prime. And the acceleration is always perpendicular to v, because remember Lorentz force is always perpendicular to the velocity, so our a perpendicular is in that direction. This is our a prime. And now let's say that we are looking at this system from a direction. So here is the observer, and of course the velocity is going to change. The orientation is going to change. We'll get to that in a second. But let's take an instantaneous point in time where the particle is here, its velocity is that way, the acceleration is that way. And so at that time, let's say that this angle with respect to the observer of the acceleration vector is theta prime. And then I'm going to call this angle phi prime, which of course phi prime is just pi by 2 minus theta prime. Right, so that's just, those are related by pi by 2. And why are these angles interesting? The angles are interesting because the radiation power that we wrote down, this is the total power that the particle produces. But that total power is not isotropic. It's not radiated in all directions isotropically. It's radiated more in some directions and less in other directions. And actually, it's that effect which ends up producing, when you do a bunch of Lorentz transformations, which we'll get to, the actual radiation spectrum. So, what is that angular distribution of the radiated power? And you may have come across this, or if you're taking this as part of a course, you will have seen this. That comes about at the same time as when you look at the Larmor formula. That formula tells you the total power, but there's also an angular dependence. And that angular dependence of the intensity has a sine squared theta dependence, right? So it depends upon the angle with respect to this line of sight with respect to the acceleration vector. So the intensity of this radiation as a function of theta is proportional to sine squared theta prime. Yeah, so in other words, the radiation pattern has a sine squared dependence. So this is, and I've just made an angular or polar plot of the intensity as a function of this angle. And at theta prime equals 0, which is along the acceleration vector, there's no intensity, and you get maximum intensity perpendicular to this acceleration vector. So what does this mean? So sine squared theta prime, of course, is just cos squared phi prime. And that's this relationship. And this is just another word for this type of pattern is the dipole pattern. So this is the dipole radiation pattern. This is the same radiation pattern that a wire will make when current goes through it. It's the same radiation pattern for basically the same reason. Okay, so now this is in the instantaneous rest frame of the particle, right? So we have to talk about what happens when now this particle is zipping around at a highly relativistic speed in that direction, because all these angles in our frame, in the observer frame, are actually different. Right? They get there are Lorentz transformations involved. So what are those transformations? And we'll see that those transformations affect the spectrum. So the transformations look like this. So we have sine phi is 1 over gamma sine phi prime divided by 1 plus v over c cos phi prime. That's the transformation of the angle phi. And cos phi is cos phi prime plus v over c divided by 1 plus v over c cos phi prime. If you're trying to memorize this or remember these, just note that there is this denominator is the same in both cases. One has cos phi prime plus v over c, the other has sine phi prime over gamma. Okay, so these are the relativistic angle transformations, and these are for reference. These two are equations these two are equations 8.14 of high energy astrophysics. So you can find them and the discussion around them there. So to see what happens in the lab frame, let us consider the case where we are looking at an angle that corresponds to a rest frame angle. So I'm just going to remove this up here just to avoid confusion with our discussion of the spectrum, because this, what I'm erasing pertains to cyclotron radiation. Right, so in the lab frame, let us consider, sorry, in the rest frame, let us consider the angle phi prime is plus or minus pi over 4. So this is where radiation is emitted at an angle 45 degrees from the direction of motion or with respect to the acceleration vector. And so that corresponds, of course, to cos phi prime of 1 over square root of 2. And the intensity, why did I pick that value? Because that's the value where the intensity is half the maximum intensity, right? Because the intensity has this cos squared, sin squared theta prime or cos squared phi prime pattern. So at an angle 45 degrees with respect to the acceleration vector, or with respect to v, 45 degrees ends up being in the same place, gives you an intensity that is half the intensity of the peak intensity. In that direction, the intensity that's emitted is half of the intensity in the peak direction. So for that value of phi prime, what is the value of phi? What is the corresponding angle in the observer frame? So for us, you just use this formula to convert sin phi prime into sin phi. So sin phi is 1 over gamma, and then we put in sin phi prime, which is also 1 over root 2, divided by 1 plus, and then v over c, which is just v over c still, and then 1 over, then cos phi prime, which is 1 over root 2. So if we assume, I'll get back to the v over c. So if we assume that the particle is moving very fast, which for all of our purposes actually will be the case, we'll talk about ultra-relativistic particles. This v over c is going to be of the order of 1. This beta is going to be of the order of 1. So I'm setting that v over c to be 1 just for this exercise. So what does this give us? This is root 1 over root 2 plus 1, right? So let's just multiply and divide by root 2 minus 1 just for fun. And this will give us root 2 minus 1 over gamma, which is 0.4 over gamma, which all the numbers don't matter. The point is that it's of the order 1 over gamma. So that tells us that the radiation that we receive in the observer frame is actually, it falls to half its maximum value within an angle 1 over gamma. So what is going on here? The charged particle in its own frame is radiating into this dipole pattern, but it's moving very fast along this direction v prime instantaneously. So that means that as an observer, if you're looking at the particle and it's coming straight at you, then this phi is 0, this phi prime is 0, you see the maximum intensity. But as you start moving away from the direction that the particle is coming, so the particle is now not, let's say the particle is going this way, but you're looking at it like that way, and as soon as this angle starts becoming greater than 1 over gamma, the intensity falls off very quickly. So half of the intensity is beamed into this angle 1 over gamma, and this is relativistic beaming. This is the reason why we talk about relativistic beaming, is because the radiation gets squeezed into this angle of order 1 over gamma. And this is where this 1 over gamma comes from. This runs around in relativistic astrophysics pretty frequently in terms of observations of radiation from relativistic particles. It's because of this angle transformation, essentially. And it's an angle transformation of dipole radiation in the rest frame of the charged particle. Okay, so keep this in mind. We will essentially end up making an approximation, that is that the radiation is all squeezed into this angle, and if you're outside of this angle, you don't see any light, and if you're inside of this angle, you do see some light. And that is going to create a, as the particle goes around, it has this little beaming cone that carries around with it, into which it's broadcasting its radiation, and that beaming cone has an opening angle 1 over gamma. And as that beaming cone sweeps past us like a lighthouse, we will see spikes of radiation. We'll Fourier transform that radiation, and from that we will get the radiation spectrum of the particle. And for that requires some additional relativistic physics, which we'll get to in just a second.